titled Climate and Earth Observation, Challenges and Possibility of Satellite Missions. Okay, thanks, it's now working. Good morning. The panel titled Climate and Earth Observation, Challenges and Possibilities of Satellite Missions was set some months ago. And when we started the discussion on the content of this panel, the idea was to talk about not about the sensors, but about systems and their effectiveness. So this is the content of today. My name is Hans-Jörg Titus. I'm the board member of German Aerospace Center, responsible for space science and technology development. And I have panelists with me. I start with the first one to the left is Piers Sellers. Everyone of you might know him. He's not only the only one of us here on the podium who saw the atmosphere from above, because he spent 3 times in space. He is also an excellent scientist and well-recognized expert and brilliant scientist for climate change and global warming. Thank you for coming all the way from NASA Goddard. Thank you for that. Then is Alberto Morea, the director of the Institute of Radar Technology in DLR in Oberpfaffenhofen. He is responsible for all the radar mission of DLRs. And in X-band and L-band we have also C-band. And there is Chu Ishida, the Senior Chief Officer of Space Application at JAXA's Space Technology Directorate. He is as well an expert for Earth observation, in particular for disaster monitoring and environmental prediction. This is one of the fields we will discuss now today. And then here, last but not least, still working for the Technik is Volker Liebig, Director. Thanks for that, Volker. Director for Earth observation in ESA, well known maybe to all of you, or many of you well known. When we started this panel, I said we like to discuss the chances of observing satellites in order to control future contracts and agreements on climate control, on pollution control. So the question of this meeting is not the single sensor and the idea how sensors are working. I think we have excellent sensors, and we develop new sensors. They're all excellent. But I think we should think about the robustness of observation systems and the observation by satellites. There is a focus on the next climate conference on climate monitoring in Paris now. So I think this theme is now coming in time. We decided to give all the speakers roughly 10 minutes for an introduction, and then we like to discuss the questions. What are, from our perspectives, the major deficiencies of the current climate monitoring activities? And what is our expectations for the future development of monitoring climate change? And can we provide a rough estimate of the necessary efforts? This means financial as well as technical required to install effective climate monitoring in space within the next 20 years. There is one person is missing here on the board. It had been announced as Professor Grassl from Hamburg. He cannot show up, unfortunately, because his wife became seriously sick and he asked to stay in Germany. I think we understand his decision. He sent me last week, and so sorry for that. But now we start. I think the first one is Piers. No. No. We started with. No, we start with you, Piers. Yeah. You are the first.
All right.
Is it ready now?
Yeah, well,
no?
I think we're going to have to use
wow.
steam power.
So you miss one slide.
We've been fighting the technology all morning. Yeah, good morning, everybody. Sorry about the fight we've been having with the technology. I was going to do this with glove puppets and interpretive dance if we hadn't got this working, but we have. So, very quickly, statement of the problem. So, satellites and the off-world view is very powerful. It allows us to see the whole world as a system, and we can see how it's changed. This is Christmas 1968. You're looking at 3 billion people, minus 3, because 3 people had to take the photo. And this is the view from L1 this summer. Now we're looking at 7 billion people. It's still the same planet, so the resources have had to be stretched quite a bit. They're going to have to be stretched a bit more to, accommodate 9.5 billion people by the best estimate. And we have a fleet of satellites. This is mainly the NASA fleet. There's obviously the European and Japanese and all the other international partners' fleets. And it's going very slowly because of this computer. Actually, these things fly at 8 kilometers a second. But here they're going like a millimeter an hour. It's a huge constellation, 17 satellites, but most of them are coming to the end of their design life. So big parts of the system are due for a refresh. However, in the last 20 years, we've learned a lot. An enormous amount of data. This is just the data that's used for for numerical weather forecasts. Those big square footprints are the atmospheric sounders on the polar orbiting satellites, giving us temperature and humidity. So this is huge amounts of data that's giving us basically coverage every day over the whole world. The little yellow dots you can see around the continents are radiosondes and commercial aircraft that also report data back to centers for weather forecasting. You can see how it's an integrated system. But it turns out that now we rely more on satellites than any of the in situ measurements for weather forecasting and, of course, for climate. So what do we get out of it? Well, here's sea surface temperature, for an example. This is a merged product. It's absolutely beautiful. You can see planetary scale waves in the Pacific. You can see the Gulf Stream. This is impossible to do any other way except with a satellite. So that's sea surface temperature. To me, even more impressive is sea surface salinity. We've only been able to do this in the last few years. But if you look at this image of salinity, you can see the freshwater tongue coming out from the Amazon into the Atlantic. You can see the fresh water in the middle of the Pacific. That's because it rains like crazy over there. And also the fresh water coming down from each pole with the ice melt. The Atlantic is saltier than the Pacific because it rains less there. Now, if you know salinity and sea surface temperature, you can put it all together in a model. And our colleagues in JPL have got this ocean circulation model, which I think is great art as well. You're looking at the ocean circulation here, and it's even producing all the niceties of the eddies coming off Cape Horn. You can see the ocean eddies, and also the Gulf Stream flowing up into the Atlantic and the Kuroshio current. So there you are, a complete model of the Earth's ocean driven by satellite data. Okay, what else do we see from orbit? Well, the most dramatic changes, and it's going really slowly, so you may have to use your imagination here, are in the cryosphere. The polar ice cap, I think there's a way to make this go quicker, but if I press the wrong button, I think I'll make it blow up, so I'll just let it go. We've been looking at the polar ice cap using microwave data since 1979. And we've seen a slow decrease from 1979 to about 2000, and then a rather more rapid decrease since then, which caught us a bit by surprise. It's gone faster than the models actually predicted. We've had to adjust our models. And what we've seen is that we underestimated the rate of the thinning of the ice cap. So I'm not going to wait for that little line to go all the way across, but basically, by the time you get to the teens, between 2010 and 2015, you get episodes where the polar ice cap coverage is half of what it was in the 80s. So, some of the young people here may be able to kayak over the top of the world, in their late middle age. They can just, get in a canoe and go from Canada to Russia without stopping. Greenland it's kind of a different prospect. Here we have ice that's sitting on top of landmass, or it's just a very thick block of ice that's captured at the base. And here we have a very rapid decay due to these glaciers accelerating. So what's happening here is that the ice is melting. Some of it falls into the sea. Some of the water falls straight in the sea. But a lot of it falls down in holes in the ice, and it lubricates the bottom of the glacier between the glacier and the bedrock, and the glaciers accelerate, and shum, off they go into the ocean. So if you look at the little graph on the bottom right, you can see that every winter we have a recovery as it snows on Greenland, but every summer you lose a lot more ice mass from carving icebergs. And in general, we're losing about 250 gigatons of ice every year. And a gigaton is a big cube of ice, 1 kilometer on a side, so that's a lot of ice. Here's sea level rise. Now you can see the uptick in sea level rise from 1900 to 2000. About half of that is due to thermal expansion of the oceans, and most of the rest is due to ice melt. Now we expect ice melt to pick up, land ice melt to pick up over the rest of this century, so that sea level rise will increase, it'll accelerate, and we're expecting somewhere between 2 feet and 3 feet if you're old-fashioned, or 0.6 to 1 meter of sea level rise before the end of the century, which is a big increase on previous estimates. Now, how do you make sense of all these data? I mean, tons and tons of data from all these different places. Use data assimilation. This is the NASA model at Goddard, which is running at 3.5 kilometers. It's integrating all the satellite data, and it's basically a complete toy world. I mean, you're seeing all the convective clouds, you're seeing the snow, vegetation, ice, ocean, the lot. It's a complete toy world. It's very powerful. Looking at the climate models, we could talk for hours and hours about climate models, but I think this diagram sums up all the work that's been done over the last 20 years in one nice little picture. What it basically says is that the rate of the amount of increase in temperature that we expect over the next few decades is linearly proportional to the amount of fossil fuel we burn, how much CO2 we emit. We've got scenario, this is thousands and thousands of runs from 19 models that contributed to IPCC, and they all collapse to this figure. So you can see that where we are now, we've burnt about 500 gigatons since the beginning of the Industrial Revolution. It's given us 1 degree centigrade increase in temperature. It's very doubtful that we'll be able to slow down before 2 degrees centigrade. It would be nice, but it's very doubtful just because of the econometric sort of momentum. I think it's probably advisable that we stop before 3 because the disruption is likely to be so drastic. And 4 would be a different planet. Things we can expect. We're getting reliable, robust estimates of regional changes in climate from these models. 18 out of the 19 models in IPCC predicted future persistent drought in the Mediterranean basin. That's here. And you can see that in these 2 different indexes. And also in the American Old Dust Bowl, Oklahoma and the Great Plains, which was dried out in the 1930s. That's predicted to come back and be persistent. Another thing that we really don't know enough about is what happens to all the carbon dioxide that's emitted. We know that only about 50% of the carbon dioxide that we release from fossil fuel burning and cement production stays in the atmosphere. The other 50% get absorbed by the planet. We think about 25% goes into the ocean, into solution, makes bicarbonate, makes the oceans more acidic, and 25% goes into the biosphere, but we don't know exactly where. It would be really nice to understand these dynamics better, because that atmospheric carbon fraction is very likely to change over the future. Right now, the planet's helping us out. It's absorbing half our emissions. Is that robust? Is that persistent? We don't know. So, a couple of summary statements. Climate change is real. Somebody else said that recently. We made a lot of progress in the last 20 years in modeling and observing it. The biggest uncertainties are emissions and the carbon sinks. We don't understand those very well. And there is no silver bullet. You need a systems approach. This is complicated. So, however, there are reasons to be cheerful. And Ian Dury, who was a famous punk rocker in the 1970s, he itemized them. The international community dealt with stratospheric ozone depletion a couple of decades ago, and the decision to take action was based on science. And this is what happened. There's ozone depletion going down to 2000, and then the recovery. And we're expected to be back pretty much to where we were in 2100. And that took a lot of effort, a lot of agreements, scientists, industrialists, politicians, all working together very closely. So I'm going to finish up. We're going to be talking in the United States about how to configure our satellite system over the next 10 years. We're going to argue and fight in Washington for the next 18 months to figure out the best thing to do. And there'll be a report coming out in 2017. And we can figure this out. Thanks for your attention.
Okay, thank you very much. I'm Chu Shida. I'm a JAXA Senior Chief Officer for Satellite Applications, and it's a great pleasure and honor to be here on the same panel with such a prominent speaker like Dr. Sellers and then Boca and Dr. Moreira. And Dr. Sellers said that climate change is really real, and one of the global issues the whole society is now facing. And for the climate change, I think we need very accurate and consistent data. And it is just like for a lady to measure her weight regularly in order to control her diet, in order to keep a good figure. And so I prepared 3 slides for my presentation, and then it's going to be very simple according to the this panel guidance. The first slide is Arctic Sea change, and this is from the IPCC Assessment Report 5, and this shows the Arctic Sea ice diminishing for us, more than 40 years by combining various microwave scanning radiometers, and it clearly shows that Arctic Sea ice extent upper figure, and also ice area in the lower figure shows a clear downsizing trend. And it shows that decreasing speed is much faster than we expected. And we are very pleased to see that the yellow part comes from our AMSA-E microscanning radiometer, which are carried by NASA Aqua satellite. And we are now operating GCOM-W, AMSA-2, in order to follow this yellow data, in order to make a continued operation of the AMSA advanced microwave scanning radiometers. So it's a good demonstration how a multiple satellite mission can make a long-term consistent data set in order to shows the trend of the climate change. And a second slide is the precipitation climatology data, which are obtained by TRM precipitation radar. And in collaboration with NASA, JAXA has been operating a unique rain radar on orbit for last, I think, more than 17 years. And now TRIM PR has been succeeded by global precipitation dual frequency radar. The question is that whether the global precipitation is really increasing or remain constant. And according to the earlier model simulation, it was predicted that the whole global precipitation will increase. So we are keep watching over the global precipitation rate over ocean and land. And we don't know yet whether the precipitation is really increasing or decreasing. But we can see some trend. So it shows that it is necessary to continue this kind of satellite observation in order to find, detect the trend of the global climatology change as indicated or predicted by modeling and simulations. And the last one is the global warming gas observation. And JAXA launched the first greenhouse gas observation mission called GOSAT, Greenhouse Gas Observing Satellite, 7 years ago. And then GOSAT have been acquiring global CO2 and also methane data. And this shows the data from the 2009 to 2011. And let me see if, oh no, sorry. Is it moving? Yeah. So by comparing 2009 to 2011, it is clear that CO2 concentration increased. But GOSAT shows that very dynamic CO2 concentration temporarily and then spatially. And from the GOSAT concentration data, we can see that boreal forest absorb much CO2 than expected. And also we can see the high concentration of CO2 over a large city or even oil field. And according to the recent researchers' work in the United States, that it was found that the methane estimation, conventional estimation based upon statistical data and also institute data, they found that the methane data is actually down estimated as much as 40%. So this is the first case that the GOSAT data was used in order to verify the greenhouse gas emission estimations. And our Ministry of Environment are going to continue this mission, and we are now developing a GOSAT 2. GOSAT 2 will provide a much higher accurate data, and then GOSAT 3 in 2020 aim at estimating global gas emission verification on country-by-country scales. So we are expecting that the satellite provide great powerful tools in order to verify greenhouse gas emission data. So these 3 slides, I hope that demonstrate how a satellite can contribute to climate change monitoring and also simulations. Thank you very much.
Yeah, good morning, everybody. I will also try to go to the certain aspects of climate change connected to what we do in the space agencies, of course. So here you see some of the challenges we have in this century. It's a long list. Climate change is a very important one, and we will see some of the impacts of climate change in this century already. But it's also clear that this climate change challenge is not standing alone, it's connected. So we speak about the nexus climate change, water, food, for example, because food and water with the rising population we have will be a major issue in the middle of this century when we have almost to double the food production. And it's clear that this has also to do with what climate change is doing locally on this planet. If we want to understand climate change better, we need to understand first the processes. So what we do to do that is science, it's clear. We do also scientific missions, which are usually one-offs, to look into different parameters of the climate system and try to understand it. In some areas we have made a lot of progress, so we believe to understand the climate system. In other areas we are still a bit away from that. We have still many open questions. Piers has already mentioned on the carbon side. We have, for example, holes in our knowledge on how much biomass is, for example, in the tropical forests. We have errors in the order of more than 40% in our estimates for that, and we should try to get this down. But there are other sources and things, or atmospheric CO2. We can measure certain points in the atmosphere, but we cannot measure fluxes at the moment. We cannot distinguish with what we do between anthropogenic and natural sources and things. So we have still to understand many processes, but then when we understand the processes, we have to go to long-term measurement. So we need monitoring. And also here, I would say the only full working monitoring system on this planet we have at the moment is the meteorological satellites and the in situ measurements, because this belongs together. And I would say that we have even more gaps in the in situ measurements than in the satellite measurements. So also here we have to work to close some gaps. So with what we do in Copernicus, in Europe we try to close some of the gaps, but it's by far not all, yeah, and we will see this. So the Global Climate Observing System, I think we have seen Jean-Louis Felouz. I don't know whether he's still here, because he was the author at this time of the Global Climate Observing System, which defined 50 essential climate variables, as they called it. So these are variables we have to monitor long term, and about half of these you can get from space. Here are some selected ones, so cloud properties, carbon dioxide, for example, methane, but also sea surface temperature, aerosol properties, sea level rise, sea ice is an important issue. Chu has shown some curves of that. And so we have to try to go and put our forces together that we measure all these 50 ECVs. ESA has done that for 14 so far, and member states have given us some money for that. I show you two examples only, which are connected to that, but also connected to international cooperation, because this, I think, without international cooperation, climate change cannot be tackled. So 3 years ago, more or less, NASA and ESA decided that we should do an effort to finally answer the question, is there accumulation or ablation of ice at the poles? Because it was not completely clear when you go through all the scientific publications. And so we put our forces together and asked 47 scientists to look into 54 years of data from 10 different satellites. And now we have the result, which shows that, in fact, if you take all measurements together, there is an ice loss, and there is also a sea level rise from that. So I will show you the sea level rise curve a bit later, where we have 3 millimeter per year. But what was the result of the IMBY approach was that 11 millimeter since 1992, plus minus 3.8 millimeter, come from the melting alone, yeah, and there was another result that the Antarctic ice loss today is 3 times higher than in the 90s. So we have an accelerating issue, and we have now 5 years of cryosat data, which is the satellite able to measure sea ice thickness, another important parameter, but also the ice shields. Here, for example, in Greenland ice is supposed to melt much earlier than the Antarctic ice shield. What we could see here, the results from the IMBI experiment for the time frame of 2003 to 2008 is in the order of 190 cubic kilometers ice loss per year. But from Cryosat, from 14 million measurements between 2011 and 2012, we see that it has almost doubled in this time frame. We all know climate means at least 30 years, this is the definition, but at least this short time series give us already some insight into something which seems to accelerate. And it's also clear that with this type of results, we need also to have long-term measurements. And this is one of the challenges, is also, I think, one of the subjects of this panel. We have to make sure that this type of satellites, like Cryosat, but many others who measure other parameters, become operational satellites. We have demonstrated we can measure, we measure dramatic things, and by the way, the change of the sea ice coverage in the Arctic is probably the most significant climate change we see in our lifetime. Because until mid of this century, and it's only 35 years from now, it's estimated that in summer there will not be very much ice left at the North Pole, so that the whole area will be shippable, and this will change many things, geopolitically, access to resources, ship routings, etc. So we have to have an eye on that, because it will really have an impact also on us who are living now. This is the second example of the ECVs I wanted to show you. It's the sea level rise. I mentioned already, at the moment we have about 3 millimeters per year. In the past decades we had 1.6, so we have almost a doubling meanwhile. And it's the combination of the thermal expansion of the water column and the additional water coming from ice which is grounded on land, because ice which is swimming is not contributing to sea level rise. What you also see is, of course, there are undulations. Yeah? So we had some years, for example, where the sea level rise was much smaller. It was due to certain conditions, a combination, for example, of the decadal variation in the Pacific and La Nina. But it shows that you have a very long trend. Again, climate, we speak about 30 years and longer. And you have short-term undulations. I remember that when we issued the Cryosat sea ice volume in the Arctic every year, last year for the first time, for 4 years it went always down, down, down. And then there was 1 year, last year, where it went a bit up again. And there was a very intelligent journalist from Sun in UK, and he wrote an article, "This is the proof that climate change is complete nonsense and we should go back and buy all these cars who pollute our planet." So it was really written in this style, but climate means also undulations. Nature is not always on a linear trend. Yeah? So we have to keep all this in mind. Again, this is an argument, of course, that we have to operationalize what we measure. We have to continue to make scientific missions in order to understand the processes first. And we have to couple this also with in situ measurements. As I said, I see the biggest gaps in situ measurements at the moment. And in metrology, there is as much money spent in situ as it is spent also in space-based systems. We can, of course, also look into new methods to measure in situ. The classical approach is you have also a certain number, a limited number of measurement systems, usually complex measurement systems on ground, in governmental networks, for example. One could also look in future in other things. For some parameters, crowdsourcing might be, for example, a much cheaper approach where you get thousands of measurements from people who are just cooperative, who have fun to do that and support us. So we will see. I think there are new ways we have to go. And with that, I would like to finish my short introduction. Thank you.
Thank you.
Welcome from my side. I would like to give you an overview, very focused on the potential of radar for climate research and environmental monitoring. Best way to show this is to give you an example. This is our radar mission in the national program, TNX. It's not designed as a climate mission, but has several examples or can show us also the limitations that we have today with the state of the art, and then by that we can understand the needs for the future development. So TNX has a lot of challenges, starting with the huge amount of data. We have more than 2,500 terabytes of data to be processed, calibrated, and delivered to the scientists. So the goal is to provide this digital elevation model with an accuracy that is at least 30 times better than what is available today. Beyond this huge data amount and calibration efforts, we have here also effort in the calibration of the radar systems. So both radars must be calibrated within picoseconds accuracy, so that you have an idea. Picosecond is the time the light travels 3 millimeters. So then without that, you cannot get this digital elevation modeling, this accuracy. And last but not least, this distance between the satellites that are flying some 100 to 500 meters apart from each other must be estimated with a millimeter accuracy. With all that, we have also started the formation flight of the mission in 2010. So as I mentioned before, with a distance 100 to 500 meters, it's the first time that we had this formation flight of 2 satellites in space. Since then, the satellites are working very stable, so we have acquired all the data that we need to produce these digital elevation models. And this is what we call enabling technologies. It's the first bistatic radar in space, and to demonstrate that is a challenge. But when you do that, then follow-on missions becomes much easier. Today there are many initiatives of having bistatic radar systems, even considering different satellites. One is the master, the other is the receiver, and so on. You see here some examples of this digital elevation model from TNX. So far we have processed 75% of the data of the Earth, and the accuracy we have achieved is even better than the specification of 2 meters height accuracy. You see here all mountainous areas. The volcanoes are going up to 5 kilometers, and we expect that this data becomes a reference, as the data from the shuttle radar topography mission in 2000 has been all over these years. And this last example is to show how big the land masses are. You just see here an overflight of 200 kilometers length. TNX is acquiring every day hundreds of these images. And even though it takes 1 year to map the whole land surface, that are 150 million square kilometers. So then this huge amount of data is a challenge for the data acquisition. So then now, this is the TNX. What is the limitation? Is this acquisition capacity? So 1 year for the whole land masses. And what is the potential of radar? Radar is unique because it's the only sensor technology that has high resolution, all weather, day and night imaging capability. So no other technology can allow this, so then we are convinced that radar is a major pillar here for delivering a contribution for solving the societal challenges of global dimension. And just that you see that radar is much more than just digital elevation models. Give you here some examples. The colors are just coming from the image before and after. When you have changes, you see the colors. So deforestation, then flooding. Here the ice flow with incredible accuracy, also centimeters per day. With TNX, we can also derive the volume with the topography change, not only the velocity of the ice flow. And here also very fast changes. This is the growth of paddy rice with decimeter accuracy over time. You see here the time. Red is the time of harvest. And this is, if you think on a global scale, this is unique. So no other technology can provide this kind of monitoring. The last example is a cooperation we have with NASA to map all the mangrove areas over the Earth, and not only mapping, but deriving the height. You see the validation with the LiDAR. Also here, TandemX is very, very accurate. So then now, what is coming next? So then we have shown this potential of radar. So then what is the next step? So 5 years ago, we have joined a group of 150 scientists and asked them, starting from the societal challenges, using the models, predictions that we have to derive this next kind of parameters, essential climate variables that we need from a radar mission. And the result is this one here. We have grouped in different spheres, the biosphere, geosphere, cryosphere, and hydrosphere. You see that from all these parameters here, 7 of them are essential climate variables. But most important, you see here the time scale. This is the observation interval that we need. Some of these dynamic processes are changing very slowly, like biodiversity, some very fast here, soil moisture, flooding, deforestation, and so on. And based on these inputs, we designed a mission. This what we call TandemL is 2 satellites fly information in L-band. We need L-band due to this penetration and the high coherence between the acquisitions. It has a lot of innovations, this large reflector that allow us to map here 350 kilometer swaths compared with TerraSAR that is only 30 kilometers. We have a digital antenna, what we call digital beamforming. This I'm showing here in this slide. When we transmit, we illuminate a huge swath, but during reception, we had here a digital formation of the antenna beam. So this is done digitally in the computer. It's a new technology that is so far not available in space. And with that, we gained this huge imaging capacity. You see the comparison between TerraSAR, TandemX in 1 week. This is just a fraction of the land masses, and with TandemL we can map even twice the land masses a week. And with that we can map all these dynamic processes with the right time resolution. You see here all these parameters, and this is a revolution in the deliverable of information for this climate and environmental monitoring. So then the last slide is just to give you a vision. So then yesterday in some of the panel session was the question, what will be in 2030? So for the radar, our answer is we do believe that there will be a constellation of radar systems, similar way that we have now with GPS or Galileo. We need some 15 satellites in space, and with that we can monitor every change on a global scale every hour. And these changes are important. Today we have the communications, but we don't know what is going on. Even when there is a disaster, it takes 1 day to know what has happened in that region. And radar is unique in this sense. There are 3 different possibilities: the low Earth orbits, the medium Earth orbits like GPS satellites, and also the geostationary. And we believe this 2 orbit concepts here will be very, very attractive due to this very large imaging capability. Thank you.
Thank you. Thank you. Thank you. It's working. Thank you very much, all the speakers. And now we have another 20 minutes for discussion. Sorry for that, but with these technical problems. But before we go into discussing the questions, maybe there is questions, comments from here we should all discuss and take into account here. Is there any comment or question from the auditorium? Yeah.
I'm Daniel Rosenfeld from the Hebrew University, just 1 kilometer from here. My question is, I didn't see any any reference to climate sensitivity, that is the extent of warming for a given amount of addition CO2 or greenhouse gases. And we know that the uncertainty there is dominated by the uncertainty in aerosols, the amount of warming that the aerosols offset, especially by interacting with clouds. And we know a lot about aerosols and cloud interactions, but we don't know about the dynamics of the clouds, and to know and to actually to know the answer for that, which dominates the uncertainty in climate forcing. We need the dynamic dimension, the updraft dimension of the clouds. Is there any thoughts towards that direction?
Okay, who likes to answer this? I mean,
Okay. Well, I mean, I said already in my speech that also the interaction between clouds, aerosols, and radiation, we have a lot of gaps. We will not cover all this very soon, but at least we have one mission which we expect to launch in 2018 together with JAXA, which is the EarthCare mission. So we will look into aerosols, clouds, and radiation, and we will see how much we get also for the climate sensitivity out of that. It's not the primary objective, I have to say, but nevertheless, we will have a lot of measurements. And we will see what finally we can get from this mission.
Yeah, well, you know, aerosols, can you hear me? That's working? Yeah, aerosols still one of the biggest uncertainties in future climate change. So there is a NASA mission on the books, Aerosols in the Cloud and Ecology, ACE experiment, but that's going to go back into the decadal survey for assessment. I would imagine that some activity will come out of that. And I would imagine it would take the form of some combined LiDAR and polarimetry measurements to try and get a better handle on cloud and aerosol interactions.
Well, I have some thoughts on that, and I invite you all to come to my presentation on Thursday afternoon.
Okay.
Where I have some radical.
I will chair you from my airline seat.
Nice. Okay.
Sorry.
okay. Any other comment? Oh, there is one. Two. Okay, Frau Schmulius. And then you. No, maybe better to the microphone. It's really.
Yes, my name is Christiane Schmullius from the University Jena. I think you have all proven very well that we have lots of satellites. I mean, one thing we know we need. One thing is to look into the archives. So we have to have quick access to the archives. And we have to have a long-term availability of satellites, similar to what the Copernicus program is now doing, but for decades. But above all that, we need a concerted action between the space agencies to explore jointly the data that is available. I mean, in the way that what Piers Sellers has shown, but between agencies. So what are the concrete actions or steps? What is guaranteed for human mankind, how to have access to the data for models jointly?
Well, there's two things there. I think there's access and there's accessibility. So, you know, for a long time we've had open access to NASA data, but that doesn't mean it's been accessible to many scientists. It required a huge investment, many postdocs, to just interpret a few images. So we think we're getting better at that, but it's going to be a continuous dialogue between the science community and the data providers. And the problem is going to get actually more difficult with the more different data types and the sheer volume of stuff that's out there. But luckily, you know, the equipment is getting better and cheaper. So I'm optimistic.
Volker? Yeah.
Yeah, thank you. I would also like to say that I have apologized because I have to leave in 2 minutes, more or less, to another meeting. So what you mentioned is a very important issue. First, cooperation. I think we cooperate quite well already. We have a much closer contact now. We have CEOs where we every year harmonize our programs and we look into gaps and we look into what we are doing. So the communication is much better. We also work almost everywhere together. I can show you, tell you, for Copernicus, for example, the instruments we have cross-calibrated were useful. Landsat sensor and Sentinel-2 optical sensor are cross-calibrated. So you can really use the data together in future. What is still a problem is long-term archiving, I confess. In ESA, we have made a first step. I have to say, I was successful to bring in a budget line in what we call our mandatory budget, which is a bit solidarity budget of ESA, because nobody likes really to pay for archiving, but people see the cultural heritage and the necessity. But the budget which we received was not enough to really keep all the historical data for long. So we can archive them, but we cannot reprocess them at the moment. This we do still from other budgets, but they are not permanently available. So here we have to work, and we need also support. In Europe, it's 22 member states who have to express their will. I think it's very important that we keep this data, that we always reprocess them. This is, many people forget that they have to be reprocessed, because you have to make them available in a format set and processed with the latest algorithms to use them together with the new data. And this is really a challenge with the increasing amount of data. On the other hand, IT helps us. Piers said it. So the costs for computing go down constantly. And so it's more or less a constant amount by that, even with the rising number of data.
Okay. There was another comment. Yeah, please go to the microphone, yeah.
Morning, it's Alessandro Volpi from Skoltech. I have a question. So all the satellites, well, on the technology side, basically you're making reference to institutional missions, and you already have a big challenge with those, right, with this data. But there is an opportunity, perhaps, to also consider commercial spacecraft, right? I'm thinking on these commercial constellations that also generate data. How do you see them? And for example, what's your opinion on the difference in quality for some products, right?
Yeah. Alberto.
So then perhaps let me add that this TendenX mission was a step in this direction. It's a private-public partnership. So then the industry is making investments, is taking over the commercialization of the data. And I do see this if you separe in two classes of missions, the more focused missions with small satellites, low cost. These are predestined to be a kind of commercialization there. They will need some support to start up the business. But the large missions that are covering a large spectrum of applications, they are not appropriate for this business. They are too expensive. You have seen the discussion on the operations. They are still too costly, the operation generation of products. But the small satellite business is coming. So there are many sessions in the conference, and they are really coming more and more a case for the commercialization. And the data can be used for environmental monitoring, climate change as well. Sure.
Okay. Do you like also to comment?
No,
Okay.
I fully agree with Dr. Morera. And I think we have to mobilize all kind of data in order to address climate change.
Okay. Okay. So maybe we can use the last minutes. We have still 10 minutes to answer the questions I initially asked. And the question was, first of all, what are the major deficiencies of the current climate monitoring activity? Some of these questions have been answered or given some answers. Maybe we have additional comments from your side to this question. Yeah?
Yes. From our Japanese perspective, I think the most significant deficiency for us is a lack of commitment to long-term observations, and because of the budgetary and then policy problems.
Okay. Any other comment to this question? And you have told a little bit about the deficiencies.
Yeah, I think there's two areas that we really need to have become recent worries in climate change.
Yeah.
I think one is the carbon cycle we've been talking about, is we don't really understand all the sinks and sources, so that's one. And the other is, of course, this rapid changes in the Arctic boreal zone. So we need some resources there to look at changes, freeze thaw, permafrost, regrowth, methane, all those things up in that very rapidly changing zone.
Yeah, so this needs international research, of course. I think the major challenge now is to find ways to bring these systems to a global network of operation to monitor, not only to monitor, but also to guard and watch international contracts. I personally think that we don't have any contract on international conferences without control. And are these instruments we have ready to get this, to be this kind of control systems? That's the question.
Not yet. I think we've demonstrated the technologies that could get us there.
Yeah.
And it's not just an observation problem. It's also an inversion and modeling problem.
Yeah.
So we've made a lot of progress in the last few years, particularly, for example, CO2, GOSAT, OCO2. We're now being able to get some inversions. We can look at continental scale sinks and sources. But to do the kind of work that you're talking about, which is verification, we need to do a lot more than that.
Okay.
So technology's there, we just need more of it.
Okay. We'll go to it.
Let me just follow this example of the biggest program of UN for combating the climate change. That is the RED program, reductions of emission from deforestation and forest degradation. And for that program, there is not yet a solution based on the satellites, how we are going to manage that. So then we need this data continuity. In Europe, we have this Copernicus programs. Focalibet is not here, but this I see a very important part of this program is the data continuity. So then there is a long-term approach, 20 years, where the data will be delivered. But we don't have this kind of continuity in the science missions. The Earth Explorer image missions, they are single event. So then they are so important, they are so successful, but there is not a long-term perspective. And I think this is a very important issue to start the same kind of data continuity approach for the science-driven missions.
Yeah, I think with the advance of the technology, we can see the climate change, happening, and we are going to see a new phenomena which can be monitored and also which were predicted by modeling. So the observation can provide a means to verify that what prediction made, former.
So we come to, I think, a very critical question. Is this concerning the resources? Are they enough? Are really enough? Do we need more money for that? And we need always more money. But
Are you talking about my salary?
But the question is, what are our expectations of the resources we really need to get an effective monitoring system? Because we need it one day, not so far from now. And the question is, what do we talk about? That's my question to you, and maybe you can also answer if you have any idea. I think we need much more money.
I would agree, besides our pay. I think there's two things. One is a lot of the systems that we've been relying on that have taught us so much over the last 20 years are getting old, and they need replacement. So that's one thing. On the plus side, there's more international partners out there who are joining the business, so we can share the burden. And then again, on the minus side, the problems are more complicated than we thought. So you need a systems approach to understand these things, and that means lots of different kinds of observations. So it's, I don't know, probably twice as much as we're currently investing. Rough guess.
It's a number.
Well, this coming from the agency side is probably easier for us to speak about the costs. At least my perspective is that the space is still too expensive. So then satellite missions are too expensive, operations are too expensive. And I have two good examples. The Terrazar and TANEX mission, the second satellite, the budget was as low as 60 million euros as a fixed price contract, including the launch. This is something that was feasible at that time due to this private-public partnership. For the future, we don't have this kind of trend, even in our national program anymore, what is very disappointing from my point of view. But we should not forget that there will be some competition in the future. And the example of OneWeb is the best one, with a constellation of 600 plus satellites, each satellite costing 1-2 million euros. And it will be, if everything is successful, the first time that we have a serious production of satellites. So every day, 1-2 satellites being produced, and by this, costs can be much, much lower. For science, we are far beyond this dream, but I'm convinced we need to make efforts to make the space industry more competitive.
And we have a budgetary problem, and then we have a very difficult in order to even maintain the very basic operation like advanced micro scanning radiometer now. So we had to make clear what mission is very unique and then had to be taken care of by satellite. And then satellite had to complement other data and information. And then we had to identify which has a higher priority and how to allocate our budget according to the priority.
Okay. Now we come to the end, but before we close here, I'd like to open the floor again and ask, is there any question or remark to what have been discussed and we've seen today? It's not the case, so that brings me maybe to my very last question. Have we to be faster to go in space? Have we to be faster to go in space? Because we need a long planning time for all the satellites we have, up to 10 years, to bring up a methane mission, for example. Now we have one example in Europe. And the question is it too long? How we can accelerate? Maybe this is another question we have to answer from a technological side of view.
Yeah, so today each satellite is a unique development. So everything, the bus and so on, and only possibility is to make it more modular. So like the automobile industry, they do every 1 year, 2 years a new model. Changes are small, improvements are going on, and I think we need a roadmap. At least for the radar side, we try to establish this roadmap to make small developments, and by this to make each satellite development faster.
I think there's another way to do this as well, and that is to accept more risk. So for some of the Earth science missions, accepting more risk, going to Class D, you can drive down costs and go quicker. And the other opportunity for all of us is space station. Putting instruments on space station saves you a lot of headaches, and we've managed to get a couple of things up there within Rapid Scat and CATS within 2 years of starting the project, getting something up there.
But we close at 24.
Well, I don't know.
Yes, I think international cooperation become more and more important in order to accelerate coping with the climate change, with the various missions and the various technology, and then also mobilizing all the possible means, including modeling.
Okay, thank you. I think time is over, unfortunately. We could discuss a long time, but thank you very much for your patience and at the beginning, and thank you to all. And in particular, thank you to our panelists here, the speakers, for their contributions. Thank you very much. And close session.